Hello everyone! Welcome to MOOC Iteration 16, the massive online open course from the University of Nicosia's master's degree in digital currencies. My name is Andreas Antonopoulos and I will be your teacher for today. Today we're talking about the Byzantine generals problem and all of the related technologies as our introductory second session for the Welcome. I hope you've done your homework and read the material. This is a pretty heavy chapter, and I'll go right into your questions. Let me know in the chat if you can hear me okay, if you can see me okay, and if we're all ready to go. I see we have participants from all over the world checking in on the chat. It's so nice to have you all here, and I'm so happy to be doing this for the 16th time. Okay, it took approximately 20 seconds before someone commented on my beard. Yep, it's a slightly different look. We're doing the pandemic beard. So thank you so much for noticing that. Our first question comes from Dorian. Dorian asks, is the Byzantine generals problem a variant of the prisoner's dilemma problem? And if not, how do they correlate and/or differ? In addition, do game theory concepts apply to the concepts of mining and consensus, or are they rendered from different fields of thought or mathematics? That's a great question, Dorian. I think you've hit the nail on the head. The mining and consensus systems that are used in Bitcoin and many other systems are game theoretical systems. So game theory does apply. In fact, this mechanism of incentives and punishments, risk and reward that operates in Bitcoin mining and in following the consensus rules as a whole is absolutely game theory. And all of the findings of the area of mathematics in game theory apply to mining and consensus. I like to call this general concept a fairness protocol. A fairness protocol is a mechanism by which fairness is achieved, not through enforcement, but through risk and reward. So that's a game theoretical model for achieving something. And Bitcoin's mining system is a fairness protocol. So game theory applies. Now, how does the Byzantine generals problem relate to the prisoner's dilemma problem, or does it relate? They're not the same, and the Byzantine generals problem is not a variant, as far as I know, of the prisoner's dilemma problem. In the prisoner's dilemma problem, you have two people who have common interests and but are isolated from each other in terms of communication. And if they simply follow the most obvious choices, they will end up with an outcome that is least optimal for both of them. In the Byzantine's general problem, you have, first of all, more than two parties, and secondly, those two parties are in communication, but their communication cannot be guaranteed. Even more so, they don't trust each other, and they have common interests again. But so it's similar, but not a variant of the prisoner's dilemma problem. Some game theoretical concepts can be applied there. I'm not a game theory expert. This is not an area of expertise I have, and so I can't tell you how the game theory math works out for the Byzantine generals problem, but they are related. All right, let me check in the chat and see if everybody can hear me okay. Everything sounds good. Excellent. Our next question comes from Universal. Universal asks, must every mining node download the entire chain? How is this scalable if the blockchain keeps getting longer and longer? That's a very astute question, Universal. And the answer is, it's not very scalable. And yes, every mining node, in fact, every node that wants to participate fully in the consensus system must download the entire chain. And this is called the initial blockchain download, or IBD. And one of the things that Bitcoin especially has tried to optimize over the past 10 years is the time it takes to do the initial block download. So from Genesis block all the way to the present, and making sure that that doesn't explode in difficulty. What's really interesting is that the developers have managed to keep it so that a well-equipped computer, and this is usually a CPU bound problem because all of the signatures have to be verified, a computer with enough CPU and a decent network connection can do the initial block down in anywhere from 6 to 8 hours. A less powerful computer may take 3 or 4 days, and a very, very low-powered computer, like a Raspberry Pi, might take 2 or 3 weeks to do initial block downloads. What's interesting is that the developers have managed to maintain that time, even though the blockchain has been getting bigger. So essentially, the time has been relatively steady with new technology for the initial blockchain downloads, even though the blockchain keeps getting longer and longer. This is the primary question behind the scalability debate. Blockchains are not easily scalable, and to keep a full archival node that keeps all of the information from the very beginning takes a lot of disk space, and to do the initial bootstrap from the Genesis block takes a lot of time and bandwidth. And this is why we can't just have unlimited blocks. This is why it's not possible to do on-chain scaling at the level that we might want to. We'll talk about that in future lessons. All right, George asks, how many gigabytes of information is stored in the blockchain so far? Assuming the massive storage of information, how long does it currently take for the client software to download the blockchain? What prevents computers from crashing? What will prevent this from happening in the future as the blockchain grows even bigger? A similar question. I don't remember the exact number, but I think at the moment we're looking at somewhere around 360 gigs of data on disk. It depends on whether you're keeping a full index of transactions to make your node be able to find transactions quickly, or if you're simply keeping the blocks in order to validate the blockchain until the current time. So the amount of disk space, it's not really that much. If you consider that you can get a terabyte disk for about $50 and a relatively fast SSD or similar disk for not much more, that's not a lot of information. 360 gigs isn't too bad. It's growing at a rate of 2 to 3 megabytes every 10 minutes. And as I said, it takes approximately 6 to 8 hours for a powerful computer to crunch through all of that. It's not the downloading, it's the verification of signatures that takes the most time. Obviously, downloading 300 and some gigs of data you can do relatively quickly if you have a fast connection, but then validating that information is going to take longer. What prevents computers from crashing? Simply enough, your computer can crash, run out of disk space, stop validating, etc. One of the interesting things about the Bitcoin protocol is that your computer can simply resume from where it left off, meaning you can leave the network and rejoin later and catch up and only download the difference of what happened while you were gone. This is a fundamental principle of Bitcoin. Nodes can leave at any time and rejoin the network and be able to validate up to the current state. In fact, you will read that, or more or less that sentence, in the white paper. Nodes can join and leave at any time. So even the nodes that are trying to build a complete picture of the blockchain from the Genesis block, they can join and leave several times. They can crash, come back, and pick up from where they left off. I've actually had to do that, where I started syncing a node, filled up the disk space, crashed the node, had to go upgrade the disk, copy all of the data that I'd already validated and downloaded to a bigger disk, give myself more capacity, and restart. And it started from right where it left off. So that's a pretty good design. Arva asks, what are the responsibilities of a Bitcoin full node? What does a Bitcoin full node do in ground reality? Does it need to be active 24/7 for syncing process? Also, for verifying a block mined every 10 minutes, do all nodes to be active, or do the active ones at that point of time verify? Great questions from Parva. The term full node has multiple definitions, so it really depends on what you mean. So we really break that down into two categories. The first is a fully validating node. This is a node that validates every new block and transaction as it comes in. That is compared to a lightweight node that relies on other nodes for full validation of the blockchain. In order to be a fully validating node, you need a copy of the blockchain so far. You don't need to keep all of it. Once you've validated up to a certain point, you can discard older information, a process called pruning, so you can save some disk space. But you do need to start from the beginning and validate all the way up to the current point, and that makes you a fully validating node. There's another type of full node, which is a full archival node. This is a node that has a full copy of every single transaction that has happened since the Genesis block. So it doesn't ever prune anything, it keeps the full 360 gigs. That's usually what people mean when they say a full node. In Bitcoin, a fully validating node and a full node's not a huge difference, really. They both have to download that initial information. In other blockchains, however, there is a very big difference between a validating node, Ethereum is a good example, and an archival node that keeps a copy of every event that has ever happened. In Ethereum, it is, in fact, quite difficult to run a full archival node. You need a lot of resources, and it needs to be very carefully configured. Whereas you can bootstrap a fully validating node in a matter of minutes. The node does not need to be active 24/7 for syncing in and of itself. It can go offline and come back online. I'll give you an example. I run a little node on a mini PC, and when I travel to a different city, I'll unplug it, leave it in a suitcase, sometimes for a week or 2 weeks or 3 weeks. The longest I left it recently was a month. All of August, my node was offline. Came to my new location, plugged it in, turned it on, and it just synced up in a couple of hours up to the current state and continued operating as normal. So for the blocks that come out every 10 minutes, in order for those blocks to reach the miners, they have to be propagated across a network of validating nodes, and those nodes need to be online to validate each block, each transaction, and propagate it to the miners. The miners need to be active, of course. They need to be online at all times. But your node that you use at your home that isn't supporting, real-time e-commerce or a real-time massive wallet like an exchange would, does not need to be online all of the time. In fact, you could connect it just a few times a day and catch up every now and then. And you don't need to be active in order to receive Bitcoin. That's a key concept in the Bitcoin system. So your node doesn't need to be online. You don't even need to have a node to receive an address. All right, let's take a quick break, check in with the chat and see how things are going, and I'll take a sip of coffee while we're at it. Iraj asks, what's the purpose of the nonce in the mining process? When constructing the next candidate block to be mined, we must set a nonce as a random number. And it seems to me that the nonce is an unnecessary step in the mining process. Am I missing something? In fact, the nonce is the most important step in the mining process. And let me explain why. If you take the block header and you hash it, you will get a specific result. The nonce is part of the block header. Let's keep it simple. Let's set the nonce to 0. You take the block header with the nonce inside it set to 0. It's an 80-byte block header, and you hash it, and you get a hash number. This is the output of the SHA-256 hash algorithm, the input being the 80 bytes of the block header. So now you've got your hash. Does that hash give you a winning block? Unless you're the luckiest person ever, although it is possible, it's like hitting the lottery 20 times in a row, you would not, on your first hash, find a solution that meets the difficulty target. So what that hash has to look like is a whole series of zeros at the beginning of the hash, which by chance you might happen to pick. Just like if you walk up to a gambling machine and you pull the lever, you might get all cherries on your first pull. But you probably won't. So the mining process is trying to get a hash that begins with a lot of zeros. The more difficulty we have in mining, the more zeros you need at the beginning of the hash. And if you ever find a hash for your candidate block that has that series of zeros in the beginning, you win, you submit that block, and everybody accepts it as valid. So if you put nonce as 0, you get a hash out. Now, if that's not the winning hash, you need to change something in the block header to get a different hash result. If you just hash the same thing, you're going to get the same result. It's like a fingerprint. Every time you hash the block header, you're going to get the same result unless you change some data in the block header. Well, you can't change the block version number. You can't easily change the timestamp, although we'll see you can use that as well. You're not going to change the transactions. You're not going to change the previous hash from the previous block because that's the parent. That stays the same. What is there to change? The primary thing there is to change is the nonce. So you have to pick another nonce. Which nonce? Doesn't really matter. For convenience, let's say 1. So you set the nonce to 1, and then you hash the header again. Now you get a different hash result, a completely different hash result. You only change the nonce from 0 to 1, but the result of the hashing function is going to be completely different. Does it have all zeros at the beginning? If it does, you win. Done. If it doesn't, you need to change the nonce again to produce some variety in your hash result. So maybe you set it to 2 and you hash again, and then you set it to 3 and you hash again, and you set it to 32,768 and you hash again, and you set it to 5555555 and you hash again, and you can keep doing this. Eventually, you're going to run out of options. And in fact, with today's mining difficulty, you are very likely to go through the entire 32 bits of nonce from 0 to 4 billion without finding a hash that actually has all of those zeros in the beginning, a valid hash. At that point, you need to change something else as well as the nonce. Usually, you'll advance the timestamp by a few seconds because some time has elapsed, and then you can start with all of the same nonces, 0 through 4 billion, and now you're going to get completely different hash results. Maybe one of those is going to be your winning result. Sometimes that's not enough. Maybe you need to shuffle the transactions in the Merkle tree, or change the Coinbase slightly and use the extra nonce space that's in the Coinbase, and then you can hash again and try another 4 billion nonces, and so on and so forth. So if you think about the number of hashes per second that your mining machine is doing, and how many seconds it's going to take to get through 4 billion nonces, not very long, and then you see why the nonces, first of all, necessary to create change, but not sufficient to create enough change that it will be enough to find a winning block. I hope that explained that. I would encourage you to try to keep on topic in the chat. If you have follow-up questions, please ask them in the chat. If you want to discuss some of the answers I'm giving, or you want to have some other topic of discussion related to today's subject, because if you're having all kinds of different discussions, you're just distracted from today's course. Tamari asks, chameleon hash functions, can they be used in any kind of blockchain? Yes, absolutely. In fact, I think there are blockchains that use chameleon hashes. There are also blockchains that use many different hash algorithms. So they cycle through different hash algorithms, and they do that in order to prevent the development of application-specific integrated circuits, meaning ASICs, meaning mining specific hardware for that hash function, so that it remains competitive and it can be done on GPU and doesn't require specialized hardware. So some blockchains do that on purpose. All right. Victor asks, is a 6.25 Bitcoin block reward from one block totally the same as another 6.25 Bitcoin rewarded from another block? Are we actually able to track back to each individual block later? That's a great question, Victor. Yes. First of all, it's not going to be just 6.25 because there's also the fees. So the reward is made up of two parts, the block subsidy, or the mining subsidy, and the fees, the transaction fees. So usually it's going to be something like 6.261234 Bitcoin. And that will be 6.25 plus the sum of all of the fees and all of the transactions that are included in that block. And that is encoded in the Coinbase transaction of that block. The Coinbase transaction pays the reward, the block subsidy plus the transaction fees, to specific addresses, or a specific address, which is the address of the miner. To keep it simple, let's assume you're just a solo miner. Then you have your wallet generate an address, put it in the candidate block to receive the reward, and then try to make that candidate block valid by finding a suitable nonce that produces a suitable block hash, etc., etc. So if your candidate block becomes valid and you propagate it and it gets recorded on the blockchain, everyone will see in the Coinbase transaction it pays Victor's address, or whatever Bitcoin address that is. And you, Victor, as the miner, put that address in there. You wrote a check that said to Victor's address 6.261234. And that check isn't really doing anything for you unless that becomes a winning block and gets recorded. Once it gets recorded, 100 blocks later, you can cash that check. Now, that's going to have a specific transaction ID in it, the transaction ID of that Coinbase transaction. And you can trace any payment from that Coinbase. Maybe you go out and you buy a TV with your mining reward. So when you buy the TV, your wallet constructs a transaction that says from the Coinbase address where I got my mining reward to the merchant that's selling me the TV, send the amount of the TV. Now the merchant could say, okay, where did this come from? It came from this address. It came from this specific transaction ID. And where is that transaction ID? It's in the Coinbase of this specific block. So the rewards are distinguishable from one another. You can always track them to a transaction ID that is being spent in the transaction, and that transaction ID is the Coinbase transaction. Mahmoud asks, when two blocks are transmitted to the chain at the same time, when exactly is the block reward awarded to the miner? Will that be directly when the block transmitted to the network or after approving it from all nodes? So this goes slightly to the answer I gave before. It doesn't matter how many blocks get transmitted to the network, but if a winning block gets recorded on the blockchain, it takes 100 blocks before you can redeem it, meaning that if you think about it in terms of confirmations, the Coinbase transaction in that block has to have 100 confirmations before it can be spent. So that means there are 100 blocks on top, well, specifically 99 blocks mined after that block, and only then can you spend it. There's a reason why miners have to wait longer to spend their Coinbase, and that's because, of course, miners have the implementation of the consensus rules, and if they essentially cheated to rewrite the chain for a few blocks and they'd already spent the Coinbase, we'd have a problem. So they have to wait until that block is buried deep in the chain, 100 blocks deep. If there are two competing blocks for the same position, only one of them will eventually be accepted by the network. That's called a consensus fork. It happens once a week or once every 2 weeks on average, and it gets resolved within a block or sometimes 2 blocks. And one of the 2 blocks wins, the other one disappears completely and never gets the reward. And because right on the surface of the blockchain, the top 1 or 2 blocks are always a bit fluid, they might get rewritten. That's why you say, let's wait for 3 confirmations before we accept a deposit in an exchange, or 6 confirmations if it's a very large amount, and why miners have to wait for 100 confirmations before they can spend their Coinbase. The deeper it is in the blockchain, the more confirmed it is, the more sure it is. And if you think about it, the first 1 or 2 blocks are really a bit fluid. Andreas asks, how can a winnings block's hash be verified if the verifying client nodes don't have the hash? They didn't mine the block themselves. They do. So if you're presented with a block and you want to find out if that block is real or not, what you do is you take the 80-byte header, which contains the nonce, the timestamp, the root of the Merkle tree of the transactions, the link to the previous block, and all of this other information that's in the header, and you hash it. Well, what should the result look like? It should be a hash result that has a whole bunch of zeros at the beginning. And in fact, the more zeros it has, you know, the more rare that hash is, the more difficult it was to find that specific hash. And you know that in order for a hash to be produced by that combination of the block header, the only way possible is for someone to have tried trillions and trillions and trillions of nonces and permutations of the block header until by chance they found one with so many zeros at the beginning. Essentially, that proves they did the work. You're not verifying that they find a specific hash. You're verifying that the hash that they found has a specific pattern, and that pattern is lots of zeros at the beginning. If you plug in the header to the hash function, you're going to get that block's hash. And that hash can be anything, really. But if it's a valid block, it will follow a pattern. And that pattern will be lots and lots of zeros at the beginning. And if you look at it, you can say this required trillions upon trillions of calculations or hashes to be performed in order to find this magical number. The combination of nonce and everything else that produce this hash with lots of zeros. So you can verify that the work has been done. The block header that produces a hash with lots of zeros is proof that work was done, because you can't pick a block header that produces a desirable hash. You have to try at random again and again and again until you find one. Universal asks, what happens when 2 miners confirm blocks at about the same time? It's a great question. Follow up to what I mentioned earlier. This is called the consensus fork. Let's do the diagram. Here's a miner in Canada. Here's a miner in Australia. They are working on candidate blocks, and they both find the solution that is valid at almost the exact same time. Let's say a few seconds apart, 3 seconds apart. Now, this candidate block is going to look very different from this candidate block, simply because the miners have included about 2,500 transactions in their block, most likely, and they've put a timestamp, they've put a Coinbase transaction that has their own address. All of these things are going to make these blocks different. And remember, with hashing, 1 bit of difference is enough to get a completely different hash. So when they have 2 candidate blocks that they've produced independently with whatever transactions they put in whatever order and with their own address, they're not going to find the same winning hash. They're going to be 2 different blocks that both are valid for the exact same height in the blockchain, and they have a valid result of proof of work. They have a block header hash that has all zeros to the required difficulty in the beginning, and they're both perfectly valid blocks. So they find them within a few seconds, and then they tell all of their neighbors, and then their neighbors tell all of their neighbors, and then their neighbors tell all of their neighbors. And so the 2 transactions the 2 blocks start propagating across the network. Now, as they propagate across the network, each node that receives this block will say, yep, that's valid, and say, okay, this is the new winner. As you can see, that's going to create 2 different answers. On this side of the network, as the block propagates, all of these nodes will say, this is the winner. The Australian block is the winner, and as it's propagating over here, they'll be like, oh, the Canadian block is the winner. At some point, they're going to meet in the middle. Some of the nodes are going to receive the Australian block first, call it the winner. Some will receive the Canadian block first and call it the winner. Then they might also, after a few seconds, receive the other block. And they say, oh, too late. I'm not going to accept the Australian one because I already got the Canadian one and it's a winner. And the other side is going to say, I'm not going to accept the Canadian one because I already got the Australian one, it's the winner. Now the network thinks that two different blocks are the winners. And there's a fork in the blockchain. But it's a one block fork, so it's forked like this. They both have the same parent, and the two children, both valid, are good. Now what happens next? All of the miners who receive the Canadian block first are going to start trying to build a solution on top of it. All of the miners who receive the Australian block first are going to start trying to build a solution on top of the Australian block. So some of the miners are going to try to extend this branch, and some of the miners are going to try to extend this branch. And as they work, one side is going to find a winning child first. Let's say that the miners who are working on the Australian block found a winner first. As soon as they do that and they start propagating that winner validates the Australian block as the winner of the previous round. Then this chain, which contains the Canadian block, is shorter. It has less cumulative difficulty, and therefore it is discarded by everyone on the network. The child of the Australian block will propagate to everyone. All of the people who thought that Canada won the previous round will go, oh, seems like this Australian block has an even longer chain attached to it, one more child, therefore it wins. So I'm discarding the Canadian block. I'm accepting the Australian as the winner of the previous round, and its child as the winner of the current round. Now, theoretically at least, you could have this happen twice in a row. 2 blocks found, and then 2 children found. Then what happens? Well, again, the race continues, and then the third, the grandchild, will decide. The chances of continuously finding parallel blocks decreases exponentially with each block that passes, so that way these get resolved within 1 block, sometimes within 2 blocks. A 2-block consensus fork happens once every few months, and a 3-block consensus happens once every couple of years. I don't believe we've ever seen a 4-block consensus. All right. Now we have a whole bunch of questions about hashes, hash collision, and quantum computing, which I'll get to in just a second. Let me check in the chat and see how everyone's going. Excellent. A really good follow-up question from Tatiana. What happens to the transactions that were in the Canadian block? Very, very good question, Tatiana. So what happens is they gracefully get reinserted at a later time. So when the Canadian block was assumed to be a winner, for that period of time, all of the nodes that assumed it to be a winner took those transactions out of their mempool, the waiting pool for unconfirmed transactions, and assume those transactions to be confirmed. When they discard the Canadian block, what they're going to do is they're going to put those transactions back in the mempool as unconfirmed, and then make the transactions in the Australian block and its child as confirmed. Now, it is very likely that there will be significant overlap between the Australian and Canadian block. Let's say they have 2,500 transactions. There's a good chance that more than 2,000 of those transactions are the same in the 2 blocks, in which case it doesn't matter. Instead of getting confirmed in the Canadian block, that same transaction got confirmed in the Australian block, and there's maybe some that didn't get confirmed in one and did get confirmed in the other, and vice versa. Those just go back in the queue to wait, and then in the next round, they get mined again. So they just go back into waiting. Nothing gets lost. The transactions don't expire. They just get mined at the next opportunity. And of course, you can't have a double spending because either the Canadian or the Australian transactions got confirmed, and anything that didn't quite overlap got thrown back into the queue to wait. Hakan asks, if the candidate block content is not changing while hashing, how does the hashing process produce millions of hash numbers to match the difficulty target? The answer to that from a previous question is by varying the nonce. And when you run out of nonces, the timestamp. And when you run out of timestamps, by juggling the transactions in the Merkle tree. And when you run out of those, by varying parts of the Coinbase. There's all kinds of different parts of the block header that you can vary. The nonce being the primary mechanism, and then these other mechanisms allowing you to reuse the nonce again and again and again. The nonce is the main thing. Question 2 from Hakan. If the aim is to produce a smaller hash number than a number specified in the difficulty target, what is stopping miners to generate a specific number to achieve this rather than changing the nonce and rehashing? Because the number that you're trying to produce, that's smaller than the difficulty target, is the hash output. The hash output is a number, and the hash output has to be a specific target. It has to be smaller than the difficulty target. What stops the miners from generating a specific number? The cryptographic hash function, which, as part of the guarantees that it offers you, the cryptographic security guarantees, if you like, is that you cannot pre-select a specific hash output. You can't guess in advance. You cannot produce a desired hash by figuring out how to select the correct input. You don't know what's going to come out of the hash function. It's almost like a random number generator. So if you put data into it, you have no idea what's going to come out. And you have no way of saying, I want it to come out with a number 3. You can't do that. You're going to put the input in, and it's going to come up with an answer, and that answer is going to be seemingly random. Not actually random, because if you put the same input, you're going to get the same result. But you can't pre-select the result you're going to get. Nathan says, I hear continually that SHA-256 is so seemingly random and complex that the likelihood of it ever generating addresses that would collide is as likely as to being able to correctly gauge the number of atoms in the universe, or some other analogy. It's extremely unlikely, but not impossible. Yes, this is based entirely on probabilities. Now, these probabilities are so enormous, or infinitesimally small, depending on how you want to look at it, that the extremely unlikely is on a cosmological level, meaning that it's not just like winning the lottery. It's like winning the lottery 100 times in a row while being struck by lightning in 100 lifetimes consecutively, or some ridiculous number like that. But the numbers we're talking about are in the order of 10 to the 77. So 10 to the 77 is a number which has 77 zeros. And that number is approximately equal to the number of atoms in the observable universe. So if, for example, we said, here's a beach, pick a grain of sand. And I'll pick a grain of sand, and then we'll see if we pick the same one. Yes, it is possible that we would pick the same grain of sand on that beach, but it is so extremely unlikely. Now, instead of a beach, take the Sahara. Now, instead of the Sahara, take all of the beaches and all of the deserts on the planet. And now take all of the beaches and all of the deserts in all of the planets in the entire universe. Now take every atom in every grain of sand and every grain of everything in all of the observable universe, and you pick one of those, and let's see if I pick the same one completely by chance. So extremely unlikely but not impossible is the basis of all of the security of these systems. So the follow-up question is, as Bitcoin continues to grow and increase adoption, with more users and addresses being generated every day, do the chances of this not grow by some small percentage with each passing day? Even if the chances increase by 1/4,000,000,000%, it is still possible at some point in the future. But the thing is, it's not 1/4,000,000,000%, because a quadrillion is 12 zeros, and 10 quadrillions is 13 zeros, and 100 quadrillion is 14 zeros, and so on and so forth. And the name for the number that has 77 zeros doesn't exist. We run out of names long before we get there. And so what you're talking about is, it doesn't matter if a billion, 10 billion people are generating 10 billion addresses per second for 10 billion seconds. You are still not close. If you said 10 billion people, 10 billion addresses per second for 10 billion seconds, which is a very long time, by the way, that's 9 plus 9 plus 9, 10. That's 10 plus 10 plus 10. That's 10 to the 30. You're not even close to 10 to the 77. You're talking about a fraction of that. So we're talking about numbers so big that, again, it's not just a 1/4,000,000,000%. We don't have words to express this. I've done a video of this called "Why Can't I Just Pick the Same Private Key?" And we talk about atoms and sand and the universe and all of those things. It's exciting. What exactly would happen if SHA-256 addresses ever collided on the Bitcoin network? Those people who pick the same private key or the same address would be able to both spend the same money. There wouldn't be any problem with miners accepting their transactions or anything like that. It's just that if I know the PIN number to the ATM card and you know the PIN number to the ATM card, well, it's now a joint account, whether we like it or not. And that's how it would work with Bitcoin. If we pick the same private key, we can both sign transactions at any time, and whoever signs and propagates that transaction first gets to keep the money. It's as simple as that. So the system would continue to work. It's just that one unlucky person would end up with a joint owner for their funds that they didn't exactly invite. This, again, it is not impossible, but it is so extremely unlikely as to be practically equivalent to it possible in any universe we might imagine. So this is not the weakness in cryptographic systems. Brute forcing is always the impossible way, or the near impossible way. It's much more likely that you are not picking keys at random, but instead you make a mistake. So you don't pick from all possible keys. You pick from a much, much smaller subset, because the software that someone wrote or the hardware that someone created to pick keys isn't actually picking truly at random. That is where we find problems with cryptographic systems, poor implementations of algorithms. So it's very important that you introduce randomness into your selection, which is why you don't produce keys by, for example, a brain wallet, which is a very bad way of producing keys, where you say, let's take the phrase, Mary had a little lamb, and hash it and produce a key. People used to do that with Bitcoin. And then they realized that it's not that difficult for someone to take every word and every phrase that you might imagine, hash it, and see if somebody's using that as a key, and take their money. So if you're not picking at random, you run into trouble. If you are picking at random, the probabilities are on your side. All right. John asks, will the development of quantum computing be a real threat for the proof-of-work mechanism and the overall security on the blockchain? On the other hand, can quantum computing bring any enhancements or advancements for crypto's DeFi blockchain world? Great question, a very common question we find. Quantum computing is primarily a threat for elliptic curve digital signatures, and other types of digital signatures like Schnorr signatures and things like that. It's much easier to apply quantum computing to solve the discrete logarithm problem, as it's known, which is the elliptic curve function that's used in signatures, and to reverse that. So you can find a private key from a public key if you have the public key. However, applying quantum computing to a hash algorithm, not so easy. Hash algorithms, from what I understand, and again, I am not a mathematician, and I am certainly not a mathematical cryptographer. Quantum computing is not as easily applied to hashing algorithms. So SHA-256 is not as vulnerable, and neither is the proof of work of Bitcoin to a quantum computer as is the digital signature algorithm. So we have a much bigger problem with digital signatures much sooner once quantum computing is available. On the other hand, if quantum computing is something that is broadly available, consumer level available, then you can use a quantum computer to implement a quantum digital signature which is resistant to quantum computers. So if only a few people, agents, entities have access to quantum computing and everybody else has to do classical computing, we have a problem because the signatures that you produce with classical computers can be broken with quantum computers. But if everybody has quantum computers, even simple quantum computers, then the signatures that you can produce with quantum computers are not crackable with quantum computers. So there's that. And the other thing is, of course, not all algorithms are equally resistant to quantum analysis, and therefore you can consider more quantum resistant algorithms, just like SHA is more resistant than digital signatures of the elliptic curve variety. You could have digital signature algorithms that do not use the discrete log problem, for example, and use another formulation to be more quantum resistant. Again, not a mathematical cryptographer, so you're going to have to ask someone else about those details. In the optional hash assignment, where you take your first last name and post the SHA-256 hash in the forum, Tatiana asks, why does this show 4 different formulations? They're not 4 different formulations, they're just 4 different ways of writing the same number. The first one is hexadecimal in lowercase. The second one is hexadecimal in uppercase, but it's the same number. The third one is hexadecimal separated by colon characters every 2 hexadecimal digits. Again, same number. And the last one is base 64. So hex is base 16. Base 64 is, base 64 is just a different number encoding system. A number is the same number whether you write it as decimal, octal, binary, base 16, base 64, base anything. It doesn't matter. So we can take the same number and write it in a variety of different formats using a different set of digits or characters to encode that number. So the digits 0 through 9 for decimal, the digits 0 through 9A through F for hexadecimal, and many, many more letters for base 64, and you could keep going. You could make a number system using the Unicode system. And it is at this point that our camera just produced a low battery announcement, and the video turned off. 1 second, we're going to do some troubleshooting. Let me go to our technical difficulty screen, and I'll be right back. And we're back. Apologies for that. Can you hear me okay? I think yes. Yes, we've got good sound. Yep, looks good. Sorry about that. Let me just check. Could everyone give me a quick check in the chat so that you can actually... Think we're back? Yes, we can see you. Okay, very good. Sorry, there's a slight delay between me broadcasting. Apologies, I haven't been on this camera for several months since the last MOOC, so some teething difficulties in the technology. Fortunately, Bitcoin is much more stable and mature than my video camera. So we're back to the topic of mining pools. Mining on the longest chain, 51% attacks. Carlos asks, it's already the case that mining pools have gained over 40% of the hashing power and the members backed off voluntarily. What are the actual threats, in your opinion? Any solution in sight to not depend just on their free will? So Carlos, it is the case that in the past, mining pools have achieved 40%. Keep in mind, this is not a real threat. Mining pools are simply places where miners can collaborate. Then they do not represent ownership of the hash power. They are a way for miners to collaborate to smooth their profitability so that they don't have variable profitability. So miners can leave a mining pool anytime they like. And if a miner sees that a mining pool is acting dishonestly, causing problems with the network, well, in that case, it is in the interest of the miner to depart from that pool. Because, of course, if the pool is misbehaving and this becomes a systemic problem for Bitcoin, that damages Bitcoin's security, which damages Bitcoin's price, which damages the profitability for that miner. And so the miner has every incentive to go, I'm not working with you anymore, bye-bye. And it literally takes one click to switch all of your hashing power to a different mining pool and continue mining. Therefore, mining pools do not represent a threat. And this is often a misunderstanding. When people say 80% of the mining pools are concentrated in China, that is a very different statement from 80% of the hash rate is concentrated in China, which of course now it isn't because they banned it. So, in fact, mining pools are not a significant source of concentration. And because mining pools can operate from anywhere and they can operate with any rules they want, miners keep them honest because it's in their best interest to keep honest. Now, there are some better solutions, and those are peer-to-peer decentralized pools. There was one in the past called P2P, P2Pool, or P2 pool, which is a peer-to-peer decentralized pool that doesn't have a mining pool operator. It's a collaborative system between multiple miners with no central control. The problem is P2Pool was less profitable and less efficient than centralized pools. There is actually a proposal using a system of payment channels and I believe a state chain or drive chain or some other parallel chain to have a fully decentralized pool mechanism that is fair, that requires no trust on the part of miners to participate in. And this is still in the theoretical and planning stages. But we are not done with the research and development of either mining or pools. And we might see better solutions come out. Afroze asks, what if the most powerful rig miner processes a fraudulent transaction and forms the longest chain with max difficulty? Well, Afroze, they're going to propagate that block. The block is going to then get validated by every fully validating node on the network. The fully validating nodes are going to find the transaction that is invalid, and they're going to reject the block, and the miner will have done all of that work for nothing because no one will accept a block that contains an invalid transaction. In order for a block to be accepted, the block has to be valid, the reward has to be valid, every aspect of the block has to be valid, every transaction in the block has to be valid, the transaction must not be double spent, it must not be spending money that doesn't exist, it must follow all of these rules. The list of rules is pretty long. If you wrote it in English, you're looking at some 25 different rules that have to be followed by every transaction and every block in order for the entire block to be valid. So a block is valid if and only if every transaction in that block is valid and the block itself is valid, including the difficulty, the proof, the reward, the fee calculation, the timestamp within a specific range, the header information, the Merkle root, etc., etc., etc. So a powerful miner processing a fraudulent transaction will have wasted their time and electricity for no reward because no one will accept the block that contains the fraudulent transaction. That is the system of incentives and punishments, risk and reward, that keeps miners honest. Muvala asks, or Muvala, consider one organization has more nodes, then it becomes centralized, then they have control over the network. In the future, is there any chance of this happening, or is there no difference between banks and BTC and why we need to invest in it? Nodes do not do anything on their own unless they're mining. So nodes keep miners honest, and miners keep nodes honest. Let's consider what happens. First of all, a node is simply a computer that is participating in the peer-to-peer network. I have one in my living room on a little mini PC connected to my cable modem here at home. So I'm running a node. I, in fact, run several more nodes in a variety of locations, both in data centers or ownership as well as cloud computing environments. Now, on a cloud computing environment, it's fairly easy to launch 100,000 nodes. What do those nodes do? Well, if they participate honestly in the network, they allow us to propagate transactions and blocks. Not very useful if they're all in the same cloud computing environment. They're just bouncing transactions and blocks around on the same network. They're not really adding much, but they're also not doing any damage. If they try to lie about the network, for example, propagating a fraudulent transaction or a fraudulent block, not only will other nodes, honest nodes, ignore those transactions and blocks that are invalid, they will also stop talking to any node that propagates false information. So a node gives you a transaction. You validate it before sending it to anybody else, and you say, okay, it's valid, now I'm going to send it to my neighbors. Or it's invalid. Not only am I not sending this to my neighbors, but you're a liar. I'm not talking to you anymore. Or I'm not talking to you for 8 hours. Bye-bye. And you stop talking to that IP address for 8 hours. And that way, nodes that attempt to propagate fraudulent information find themselves effectively banned from the network for a short period of time. This prevents fraudulent information from being infected. Now, most of the time, the reason this happens is because there's a bug in the software. So if you have a buggy node and it tries to propagate something and it doesn't validate the rules correctly, usually because the rules have changed and it's older software, well, then it will propagate something incorrect, and everyone will stop talking to it. And it will find itself unable to connect to any nodes because every time it tries, it will try to propagate that incorrect information and get disconnected. So it will find itself isolated. That's how you know it's got a bug in it. One organization having lots of nodes doesn't really do anything. One organization having lots of nodes that also mine, yes, theoretically that is possible. Someone could buy up all of the miners in the world and all of the electricity supply in the world and dominate mining. The problem with that is that, one, it's very expensive to do. Not only do you need the hardware, you also need the electricity. Then you would need to produce blocks with that proof of work, and there's no way around it. You're going to have to spend the electricity and do the hashing to produce it. And if those blocks are propagating information that is fraudulent, they're just going to get ignored. If you try to take over the network and change the rules, well, those who have an economic interest will stop accepting your blocks. So you're going to mine blocks with Bitcoin rewards in them that nobody wants to accept. And as a result, you can't cash that Bitcoin for your local currency in order to pay your electricity bills. Even if you could pay your electricity bills directly in Bitcoin, your electricity provider is probably not going to want fraud Bitcoin that you produced, which the rest of the network won't accept for anything else. So this is how we keep and miners honest. Nodes can't propagate false information, miners can't mine false information, and the two keep each other in check. Centralization is not so easy to achieve in these systems. That's why they're robust. They're robust against all of these types of attacks. I love this part of the course. This is the part of the course where, as people who are new to this environment, and I remember experiencing this same experience, you start reading about Bitcoin and you're like, there's no way this is going to really be working. There must be a catch. There must be an Achilles heel. There must be a way you can break this. And then you start coming up with all of these obvious ways that this can be broken. And one by one, you figure out that, in fact, in practice, you can't break the system this way. How do we know? Well, because everybody's been trying for 12 years and have not succeeded. So you know Bitcoin is secure not because no one is attacking it, but because everyone is attacking it all the time and have very, very high incentives. Almost $1 trillion sitting on the table for anyone to grab who could break the system, and the ability to disrupt a network that is causing significant geopolitical angst among various governments for various reasons, and they want to stop it. And they can't. And how do we know they can't? Because they haven't, even though they do want to stop it. All right, and I believe that gives us an opportunity to answer the last question of the day, which comes from James. Why do you think Satoshi Nakamoto elected to remain anonymous? Because if you develop the most radically disruptive financial tool the world has ever seen that creates a ton of geopolitical disruption, every government in the world wants to see dead or in prison or both, and wants to discredit you and destroy the thing that you built. And so at that point, it becomes very, very dangerous to be known. And the smartest thing Satoshi Nakamoto did was build Bitcoin. The second smartest thing Satoshi Nakamoto did was to disappear. And that's all we have time for today. This has been the second week of the massive open online course, session 16 for the University of Nicosia's Master's Degree in Digital Currencies. I'm Andreas Antonopoulos, I'm your teacher, and I will see you next week. Study your homework, read the slides, discuss in the forums, bring up questions, and I will answer as many of your questions as I can next week. I hope you had fun. It's been a pleasure to be on this course again, and see you next week. Bye-bye, everyone.